Like you said, my name's Adam Stevens, and as you can probably see from the slide, I work at Sandia National Laboratories in Albuquerque, New Mexico, and I'm going to share a little bit of a few of the conclusions I guess we came to from a short study that we did of using Parsl alongside a piece of software that we developed called Dakota, and I'll start by if I could get the slide to change, explaining a little bit about what Dakota is and how it works. So it's open source software that we develop primarily here at Sandia. The idea is that it gives, engineers, typically analysts, designers, a more sort of well-rounded perspective on the predictions of computational simulations. And so these are things like circuit simulators, structural mechanics, structural dynamics, and that kind of thing, typically at Sandia. And so, for example, Dakota does uncertainty quantification. It tells you, given uncertain inputs, what uncertainties does that induce on the outputs. It also does optimization to improve products through simulation-based design or model calibration. And it fits into a larger framework of what we call verification and validation, which is a way that we have of sort of certifying the credibility of simulation predictions. More concretely, it's a set of algorithms for doing those things, for doing uncertainty quantification, optimization, calibration, that can be applied in black box fashion to arbitrary sort of computational simulations. And so the way it works is it runs ensembles of simulations. And so for each of the simulations, it, depending on the type of study you're doing, provides strategically selected inputs and collects outputs. And all the communication that it does with the simulation is based on file I/O. So it writes out a file that says where it wants your simulation to run, what input it wants your simulation to have. It kicks off a driver that actually runs the simulation. And then at the end, when the driver finishes, it expects to find a file that contains the results that it can ingest. And so each run of a simulation, each mapping of input parameters to responses, we refer to as an evaluation. And that driver that Dakota uses to run the simulation is developed by the user. And it's nearly always used either locally on a workstation or laptop, or the simulations are run on HPCs, which are typically kind of commodity clusters. And the illustrations there are just showing that you can use it with Dakota alongside any computational simulation. Could be a circuit simulator we're showing on the left, or some type of engineering mechanics simulation we're showing on the right, or really literally anything that has sort of parametric inputs and has scalar responses that we can collect. And so there are sort of three common evaluation strategies that people use on HPCs. And I'm listing those here along with some of their challenges. The first we call massively serial, and this is just a situation where the computational simulation is serial, and kind of a subset of that might be where each evaluation is made up of a large number of concurrent serial simulation runs. And so one of the challenges there is that Dakota itself must be run in parallel to manage work across nodes, or the user has to come up with some way of managing all the concurrent serial simulations that go into doing one evaluation. The second evaluation strategy that's quite common for our users is what we call evaluation tiling. And in that case, each evaluation involves an MPI parallelized simulation. And that's also quite common. And some of the challenges there is that, for our users, is that we as a team don't provide any robust tools to help users manage the subscheduling within an HPC job. And an emerging challenge is that the evaluations within one Dakota study may have unequal resource requirements. That is, one evaluation may take a certain number of hours or require a certain number of cores, but a different one may be have totally different resource requirements. And then the final evaluation strategy that's common for us is what we call evaluation submission. Dakota runs on the login node or mom node, or maybe on some other computing resource, and then submits each evaluation as a separate HPC job. And the main challenge there for our users is just the management of the jobs, for which, again, we don't provide a lot of help or tools. And so the reason that we looked into Parsl, the reason we're interested in looking to Parsl is basically just to provide recommendations to our users, or perhaps a set of tools to our users to help manage these evaluation strategies. And so we developed 3 examples. I won't go into all the details of the examples because I don't have time. Mostly focused on sort of the massively serial case and the evaluation tiling case. We didn't develop an example for the last one, that evaluation submission, but I'll mention just a little bit about it. Nevertheless, these are kind of the characteristics of those 3 problems. We exercised or created a demo that was just a very simple sort of driver only demo, one that involved some data dependencies, and then finally one that where the individual evaluations were MPI parallelized. And so here are kind of the conclusions of that we came to after developing and looking at these demos. For the massively serial case, we think that Parsl is really a clear win. Parsl does exactly what our users need. It's extremely intuitive to write Parsl scripts to handle to do this strategy. Skipping down to the bottom, for evaluation submission, we also think Parsl pretty much out of the box as it currently exists now could be used. It's overkill, and so if it weren't for the fact that we may want to have sort of a unified solution, we might not reach for Parsl for that reason, but it's could still nevertheless be used, and so might be Parsl might be a good tool for us for that, just because it also covers our other bases reasonably well. The middle case evaluation tiling, we found that it was useful with a couple of caveats. One is that there's currently no way to express an app's resource requirements, and so in the situation where you have, maybe one of the apps is an MPI parallelized simulation and requires a lot of resources, and some of the other apps that just do some of the pre and post processing, maybe serial. That's sort of getting those things, using Parsl to manage those things or to schedule those things is not easy, I think. And another, maybe area where we don't have good overlap with the features that Parsl provides is that there's not a lot of support for landing MPI parallelized tasks, and so that need still sort of falls to the user. And by landing, I mean, providing the right combination of arguments or whatever to srun or to whatever your MPI launcher is to get it to put your simulation on unused resources. And then for all 3 of the use cases, sort of a common need, I think, is for task sandboxing. And because very often the simulations that our users are running have potentially a large number of input files, produce a lot of output. They may not necessarily have a lot of control over what the input files have to be named or what the output files are named, and so we need some type of sandboxing to manage sort of the files for each task, and that's not a feature, as far as I can tell, that's currently provided by Parsl. And so that's just sort of I think I'm probably just about at time. And so that's just kind of a taste of kind of what our needs were, a study that we did, and some of the strengths and weaknesses or some of the overlaps and disjoint parts that we see Parsl providing for our use cases.
Okay, cool. You got 40 seconds left.
Great.
So I'll quickly ask a question. So your task sandboxing, that's like you want to do keeping files separate, or
correct,
other environments, just files? Okay.
For the most part, it would be files, but it could be actually also environments. Yeah, actually, that's a good point. I was thinking primarily of files, but we do have the situation where, we use typically module systems on our HPCs, and so we have to carefully manage which modules are loaded to avoid library conflict.